Alright, opposed to what's in the schedule, Andrew Jackson is not going to give the next presentation. Instead, Oliver Oxtoby is going to present. He's a senior researcher at the South African Institute, Research Institute, CSIR, and he's an expert in the field of multiphase flows. And together with engys, they developed a new CFD solver that's based on open foam technology in order to give better multiphase flow simulation results.
Thanks, Frank. Well, as Frank said, my name is not Andrew, but Oliver, and I'm now the newest employee of engys, and I think they decided it would be more fun to give the new guy the presentation to do, so that's why I'm here. So yes, I'm going to be talking about the Helyx Hydro code, which is an optional add-on module to the Helyx product developed by engys. And as Frank said, this was developed jointly with the CSIR, both in my capacity in my former job at the CSIR in South Africa in the aeronautics department there. And the reason for that is that the code developed, or the original application was for violent sloshing in aerospace type of fuel tanks, but it's been expanded to be a general improvement on the multiphase flow code. But before I get into that, just a very brief overview of engys for those of you not familiar with us. It's a company which provides computer-aided engineering products and services built on open source solutions. This, I feel, is the way of the future. Really, the companies want to take full ownership of the entire analysis and design tool chain that they have. And several of the founding members of the company have been open foam developers ever since its inception. In fact, before it was open foam, it was just a foam project. They've been involved from the very beginning of that. And so much of the code developed is based on this open foam framework, but it's enhanced in various ways, both solvers and libraries. So it consists of both CFD tools, which I'll talk about more, and some new joint optimization tools, and we provide support in the Dakota multidisciplinary optimization tool. The company was founded in 2009 and has steadily grown since then. The products which are available are the Helyx code, which is a general open source CFD tool. Then there's a freely available version of that which can be used to drive the plain free version of open foam. Anyone can download it and try it out. And then there's the Elements software, which is specifically designed for automotive applications. We offer, as I said, analysis, consultancy, support and training, custom development, and so on. So, as I said, Helyx is a general purpose CFD tool. The idea behind it is to have the same capabilities as the traditional closed source software available on the market, and it's really designed to be a product, not a project. It's supposed to be a useful product for a company that comes with everything that you'd expect from user support to proper documentation, regular code maintenance, binary releases that run on both Linux and Windows. Okay, so thanks for listening to the shameless marketing. Now back to the slightly more academic part of the talk. This enhanced multiphase flow solver. So just as an overview, it's based on the volume of fluid method, similar to the interfoam code that you might be familiar with from OpenFoam. The volume of fluid method is fairly simple in principle, that you have an indicator function which indicates whether a given cell is full of liquid or full of gas, and you're supposed to maintain a sharp interface between the two. In fact, the numerics become very tricky, and it's very susceptible to a lot of numerical artifacts because you have this discontinuity in density across the interface, which is typically a factor of 1,000 or so. So developing numerics based on this is often very much based on taming all these instabilities that occur. So what we've done in the Helyx hydro solver is not only to try and improve on the numerical discretization, but to take this further, add compressibility effects, thermal effects. And so there are two solvers which are bundled. Standard, basically isothermal solver, which allows the gas phase to be compressible, and thermal hydro, which includes both heat and mass transfer and temperature dependence of the various material properties. So as I mentioned, one can do both isothermal and non-isothermal flow modeling. We've added handling of arbitrary heterogeneous porosity fields, accounting for variations in the gas density, as I mentioned, improved stability on unstructured meshes, and some improvements to the coupling of 6-degree freedom models with the flow solving. So just as a kind of overview of a sort of sampling of the kind of application areas, there's violent tank sloshing, which is where it started out for kind of aerospace applications. Cryogenic sloshing, as an example, we had a client looking at space applications, improved seakeeping calculations of ships, and then one can also add multiple coupled regions. As an example, the liquid natural gas carrier here, we have liquid and gas inside a container, and then the whole ship on the sea. One can treat these various different regions of liquid and gas in a fully coupled manner. Then with the porous modeling capabilities, one can, for example, do coastal structures and treat those as structures as varying porosity. And then we've looked a bit at microgravity and microfluidics type applications where the surface tension is important, and tried to improve on the numerics in those cases. So first of all, just to focus a bit on sloshing type of applications. Some improvements that are important here are an improved interface capturing scheme, the higher fidelity that is fully second order accurate, and an improved pressure interpolation scheme. And you can see here on this this graph here, which shows a output from a pressure tap inside this shaking tank case. The experimental results are in black, and the outputs from the standard open foam interfoam are in blue, and in the enhanced code using this hierarchy interface capturing scheme are in red. And in general, they capture these peaks far better. The very high black lines are measurement anomalies, but in general, the peaks are better captured. And in this particular example, we found that some of the commercial codes struggle quite badly with smearing of the interface, to the extent that you can see what happens with the purple line of the pressure tap, that it just starts to kind of smear out into more or less a sine wave type of thing. Just to show, for this case here, a direct comparison between experimental results and numerics. Then looking at a much simpler, much less violent sloshing type of problem, just for validation purposes, a single tank with a single baffle configuration. What you find running this with interfoam on standard open foam is that the damping ratio, the dissipation of this problem is much higher than it should be. If we plot here the damping ratio of the sloshing action relative or with respect to the wave amplitude, there's some experimental results of these crosses down here, and the damping is off by a factor of more than 100% in standard interfoam. And with these improved second order accurate time integration schemes and improved pressure interpolation methods, we managed to get far closer to the accepted correlation, which is the solid line here. As I mentioned, improvements to the pressure interpolation improve greatly the spurious currents that you see in the gas phase. If you've used interfoam, you're probably familiar with these, and that's partly the cause of the excessive dissipation that I showed on the previous slide. And we've managed to improve the interpolation a bit for non-orthogonal grids and significantly reduce those spurious currents in the gas. And as I mentioned, compressibility has been added to the code, both for the isothermal and non-isothermal code. And this allows to actually predict absolute pressures in a tank, for example. An purely incompressible solver can only give you a difference in pressure between 2 points, but as you see on the graph on the right, one can make an absolute prediction of pressure. And the graph on the left just shows the difference between a kind of oscillating gas pocket if one uses purely incompressible versus the compressible code. The nice thing about this is that you actually end up with a faster solution time simply because you're basically softening up the numerics a bit. Then further improvements are adding the temperature equation and thermal modeling to the two-phase flow. We allow for both an ideal gas or a real gas. At this stage we've only got the Van der Waal gas law in there, but there's a general interface for writing one's own gas laws. For material properties can be dependent on the temperature, can be tabulated more or less arbitrarily, and the solver supports mesh movement meshes. Just a simple problem to illustrate the heat and mass transfer. This is a droplet being dropped onto a hot surface, and due to the Leidenfrost phenomenon, it kind of floats on a cushion of its own evaporation when it hits the surface. So we have a film evaporation model in here at the moment. Then in the isothermal solver, we have support for arbitrary heterogeneous porosity fields. The idea is that you can specify any varying porosity field, whether it includes sharp discontinuities in porosity or not, and the solver should be able to handle it. At this stage, it doesn't take account of capillary effects, so it can't really be used for sort of gas sparging underground, those sort of applications, something that can be added. So it's basically a Whittaker type of averaging that's done on the governing equations. You have a porosity in all the various different terms of the governing equations, and as well as a Ergun type of porous drag term on the right hand side. And then, as I mentioned, the numerical handling of these kind of discontinuities in multiphase flow just becomes even more complicated when you have to be able to cope with the arbitrary discontinuity in porosity and therefore in velocity, which intersects with this discontinuity in density and therefore gradient of pressure as well. So it's quite a delicate thing to formulate the equations in the right way that will allow, even just in a simple 1D tube like this, that will actually allow you to overlap all these different discontinuities on each other. So aside from doing those interpolations in such a way as to make that possible, you also get quite strong pressure gradients in these porous zones, and therefore it's important to relook at the calculation of the pressure gradient on a unstructured grid. It's the standard Gauss gradient is not second order accurate, so one method is to go to least squares type of gradient approach. The problem is that's not momentum conserving, so we've developed a kind of a skew corrected blend of the two that uses the least squares method to do the skew correction, and you can see just in this simple tube how that improves the prediction of the velocity through this little porous region in the middle of the tube here. So just as a very simple benchmark problem, but one of the few where there's actually experimental data available, it's basically a fish tank with a region in the middle full of crushed stones, and it's kind of a dam break problem where a partition is removed from in front of this liquid, and it sort of seeps through this partition of stones. And as you see on the left, we get a very good correlation with the experimental data. And so one example application of this is, as I mentioned, a breakwater unit with these a kind of a porous bed of armor units on it. And you just describe this as various different porous zones, the gravel at the bottom and the breakwater units all having different porosity, and just as a kind of proof of concept, you have a wave with an entrapped gas region in it hitting this breakwater at the top. At the bottom is what you'd see if you didn't have any armor units around the breakwater. At the top you can see how it kind of damps the action of the wave. Another sort of simple application example for this was a ferrosilicon smelter. You have these 3 electrodes and a large production of gas occurring under the electrodes, and this is all surrounded by a porous bed of rock burden which is fed into the thing. And as the electrodes melt this rock, you get a liquid region at the bottom, and the challenge here is to find out at what point the mechanism behind this tap hole gassing phenomenon, when basically the liquid runs out and gas starts to flow through the tap hole. So it's very hard to get actual values for the different porous layers in the smelter. You basically have to turn the thing off and let it cool down and dig it out. But using some very crude estimates, we managed to actually get values out which more or less corresponded with the few measurements you're able to take on these things, the gas crater pressure in the center and the outflow rate of the liquid from the tap hole. So, so much for the porous additions to the solver. We've also made some adjustments to the surface tension handling. It's basically a type of automatic smoothing of the surface tension force, which gives you a field which is more like a level set type of field, and this quite significantly reduces the spurious currents that you see on the liquid gas interface. And this is just an example of a little slug of water being transported in mineral oil. Then once again, surface tension type of dominated flow. This is an example of a spacecraft in zero gravity in a maneuver that is performed where the thrusters are fired forwards and reverse to try and transfer liquid from one side of the tank to the other. And this is just compared against some data we found from another code that was relatively crude. It just used purely castellated structured meshes, as you see on the left, but nonetheless got a reasonable correlation between the two codes. Then a few other enhancements that we've made to the handling of coupling between multi-two-phase solver and a 6 degree of freedom solid body. This is just a very simple case of a floating block. It's the standard floating block problem in the standard open foam release. But as you see, looking at the graph on the left, running this case with different values of under relaxation for the coupling between the 6-DOF and the fluid actually ends up with completely different results. And that's because the solution actually isn't stable in this case, but you don't realize it because you're just running it for a fixed number of iterations. So one can not realize that you're actually producing an erroneous result here. So to improve the coupling, we've just added some solution acceleration and iterative scheme with Aitken acceleration between the fluid solve and the solid solve. And the graph on the right shows, first of all, the blue line from the left is reproduced here in purple, and then the new scheme is showing with 3 different values of the initial under relaxation, all of which lie right on top of each other, so there's no longer any dependence on that under relaxation factor. So a more realistic use of that would be a kind of a sea-keeping calculation. This is a small dinghy bobbing in some waves. This particular case, if you try to run it in the interfoam solver from the standard open foam release, it just crashes because the parasitic currents caused by the large cell non-orthogonalities are not too much. So as I mentioned at the beginning, the solver was originally developed with aerospace fuel sloshing applications in mind, and it was basically the enabling technology behind a large sort of technology partnership in South Africa between Denel, which is basically an aviation systems manufacturer, the University of Pretoria, and the Council for Scientific and Industrial Research. The idea was to basically bring together manufacturing, testing, and numerical modeling. This was used, first of all, for fatigue analysis in an external helicopter drop tank. These tanks are expendable, so the idea is to get them to last just as long as they need to last, but no longer. And using the code for this fatigue analysis, one generates some quite interesting sort of very nonlinear relations between the fill level of the tank, the frequency of excitation, and the loading on the end caps. And then within the same project, it's also being used as part of a modular tank validation and prototyping system. Basically, a tank is manufactured with these windows on the side used for taking measurements and instrumented in various ways, and this is at the moment being used to validate the code. The tank is put on a large series of hydraulic rigs and shaken around, and we're going to get a lot of data out of that that's going to provide some very valuable direct validation data for the code. And so in that context, the benefits of using the Helyx code have been improvements in the accuracy and analysis time of these sort of very violent sloshing type analysis. The improved meshing technology in the Helyx product allows to mesh these very sharp and complicated shapes of the baffles inside the tank far better than the standard software. The use of open source technology allows to run hundreds or thousands of runs to explore this very non-linear design space that's absolutely essential in this case. And then an important thing in South Africa is having a very easy to use product that relatively unskilled workers can use to increase their skill levels. So finally, just future plans for this code. As I mentioned, a large part of the focus has been on improving the numerics, especially in the presence of large discontinuities in various field variables. But there's still a fairly fundamental problem with parasitic velocities that's fairly core to the volume of fluid method, even on a structured mesh, and that's something that we're doing ongoing research into. We have some very, very alpha phase software that we're developing now to try to improve that problem. Then some other enhancements would be to we don't yet have GUI support for the thermal solver that will be added very soon, and various other small enhancements that we'll be adding. So thank you very much for your attention. If you have any questions, I'll be very happy to answer them.